Hi Sec 3 Pure Physics class. This is a video recorded lesson on thermal properties, which is actually part of the topic on heat capacity. So if you go into the textbook, this is a hidden part in heat capacity. As you listen and watch, please fill in the blank in the notes, and you will end the lesson by completing the worksheet behind. First of all, thermal properties is about melting, freezing, boiling, and condensing and evaporation, as the title suggests. You have learned this in your Sec 2 science lesson. Now we will take a closer look how all these processes has got to do with the kinetic theory and internal energy. We first look at heating, and then in comparison with cooling, how the terms used are different. Okay, so let's first look at heating. And as I go down the list and I open up all these boxes, you can always pause and fill it into your notes at the same time. Okay, ready? So let's first talk about heating. In heating, you will see heating curve where temperature rise. Okay, you can see the temperature rise as you look at the heating curve here. When heating occur, melting can happen, boiling can also happen. And when cooling occurs and you can see temperature drop, you will see freezing happen or condensing happen, condensation. So let's first look at heating. When heated, a metal temperature increases. Okay? And during melting or boiling, temperature stay constant. This is a very important key point. Okay, because it says a lot about the behavior of the molecules in the metal later on. Okay, so take note, during melting or boiling, temperature stays constant, it doesn't change, and the state changes. So if there's melting, then the state changes from solid to liquid. If there's boiling, then the state changes from liquid to gas. And during this process where the temperature stays constant, that temperature is known as the melting point or the boiling point. Let's first take the heating curve as an example. Look at this heating curve here. Over a period of time of heating, the temperature rises. The temperature of the solid rises from A to B. Then from B to C, temperature stays constant. So I know during B to C, melting has occurred. The solid is melting. From C to D, then temperature rises again. So let's look at the terms used in what is happening in all this region. A to B first. In the first 3 minutes, okay, in the first 3 minutes, we can say that from A to B, energy is absorbed by the substance being heated. In the past, we used to say heat is absorbed by the substance. Now we say energy is absorbed by the substance. You can pause here and fill this in and then continue. Okay? Now next, during melting, solid would have, it would have started to melt. So you will see two states here, solid plus liquid. So during the melting process, you see solid and liquid forming. During this melting process, heat energy is also absorbed by the substance, this mixed substance of solid and liquid. Heat energy is absorbed. But now we don't call it heat energy, as you all learned in the previous topic. Now this energy is known as latent heat of fusion. So latent heat of fusion is absorbed by the substance as melting occurs. Normally the heat energy, the energy absorbed at this point during melting is much more than the energy absorbed from A to B when the temperature is rising. During melting, energy absorbed is much more. Reason why, later we look at the kinetic theory part of it. Okay? Now by the 7th minute at point C, the solid would have completely melted to form liquid. It has all completely become liquid. So from C to D, if heat continues to be applied to this liquid, then the liquid temperature will rise now. And from C to D, this region is completely liquid. So many a time question will ask you, from B to C, what are the states found? Is solid and liquid. From C to D, what is the state found? So it's liquid. So these are things that you need to know, all right, from the heating curve. And then similarly, when it comes to this heating curve on the right hand side, okay, right hand side, you can see that there is only one step. The graph is only one step, unlike the one on the left where you see one step and then it continues to go up from C to D. Okay, on the right side, this heating curve show only a one step, X to Y, Y to Z. There's no more curve to show, no more graph to show after Z. And it started with liquid. So if it started with liquid and temperature rise, when it's reached a constant temperature from Y to Z, this state, the occurrence here is known as boiling because it started with liquid. And of course, when boiling occurs, it starts to form gas. So during this boiling process, the two states that appear is liquid and gas. Normally, you also see steam appearing at the same time. So it's liquid and gas. Now again, at this point in time, I want to mention that X to Y, energy is absorbed. But from Y to Z, there is a different name. This energy has a different name. That energy absorbed is known as latent heat of vaporization. And this latent heat of vaporization, we say is absorbed. Okay, it's absorbed by the substance. Okay, at this point, I will want to continue down from the heating curve, because if you understand heating curve, you understand everything about heating curve, then the cooling curve is just the opposite, right? The heating curve is just the opposite. Okay, let's look further down below what we mean by melting point. After this entire topic, the one-page worksheet behind, we will gather some information, the definition about what is melting point, how to define melting point, how to define boiling point. But at this point, if I ask you for what is the temperature for melting point, I believe you know how to see. It is at this point when melting occurs and the temperature is 60 degrees Celsius. Now, what about boiling point? Can you fill it in yourself first? Okay, now check my answer. The boiling point is 95 degrees Celsius. All right, now below, I would like you to see the three tables I've put together for explaining what happened during heating to melt. That means we are looking only at this graph A to B, B to C, and C to D. Because if you understand this melting curve, the heating curve for melting, you will understand the melting curve for the heating curve for boiling. Okay, so let's just look at the melting curve, the heating curve for melting. Okay, now I have divided the table into three columns. First column is the physical properties, the changes in the physical properties, and then the middle column is the kinetic theory of particle to explain what is happening from the different parts of the graph. Okay, for the different parts of the graph. And finally, how this kinetic theory explains the changes in the internal energy of the substance involved. So we are talking about internal energy of this piece of solid in the graph from A to B, then from B to C, and then C to D, which is the liquid. All right. So we'll be referring to the graph as we talk about these three columns here. Again, these three columns are very, very important because if you understand it, it will help you explain everything from the heating curve for boiling to the cooling curve for freezing as well as cooling curve for condensation. Now, first of all, before we go into the third column on internal energy, let's recall, you write here, I think in between here you can write, internal energy of a substance is the sum of total kinetic energy and total potential energy of its molecules. I repeat, the internal energy of a substance is the sum of the total kinetic energy and the total potential energy of its molecules. So that's for the third column here. That's for the third column. Okay, let's start with the physical properties first, the physical part of it. From what we explained just now, what is happening from A to B, yeah? We are talking from A to B. Now, A to B, what is happening here is the solid has become hotter because temperature only rises. It hasn't become liquid. A to B is not melting yet. So the solid becomes hotter. That's the physical part of it. At the temperature, what I see, the temperature occurs to the temperature in this graph from A to B is the temperature of the solid increases. Now, talking about the energy, that in terms of energy, from A to B, again, still on A to B, the temperature rises means the energy is absorbed by the solid, by this solid. Energy is absorbed by the solid to raise its temperature. So if I ask you what happened to the energy from A to B, you have to be able to say the energy is absorbed by the solid to raise its temperature. Now, from still on A to B, let's go on to the second column on the kinetic theory. What does kinetic theory of particle explains about the temperature increases? If you recall, when temperature rises, it is about molecules vibrate faster. The molecules of the solid, because from A to B, we are still talking about the solid state. And because it vibrates faster, they are pushing each other further and further apart. Now, if you recall in your lower secondary science, when solid expand, it only expand very little. It expand, nevertheless, it still expand. The reason why it expand little is because of the very strong force of very strong intermolecular force between the molecules. So although it goes further apart, the spacing has increased, but only a little. That's why the expansion is little. Now, if you know internal energy is made up of kinetic and potential, if molecules vibrate faster, then the kinetic energy has increased. And since molecules has become a little bit more spacious, the distance between them has increased, the potential energy also increased. Remember, we mentioned potential energy is the spacing or the distance between the molecule. The further they are apart, the greater is the potential energy. Okay, so therefore we say internal energy has increased. Let me write it here. So in this case here, we say internal energy. Okay, the internal energy increases. All right, increases because both KE and PE increase. So the internal energy increases. You can fill that in your notes as well. So I'm going to explain portion by portion of the graph by looking at the physical part of it, the kinetic theory part of it, and how this contribute to the internal energy of the state, of the matter in that state. Okay, now having looked at A and B, let's look at B to C. B to C in the graph, if you look at B to C in the graph, it's about melting. Melting. Now, melting means something again. From B to C, solid is, the physical part of it is, the solid is melting and liquid start to appear. Okay, liquid start to appear. So there are two states there, solid and liquid. Temperature stay constant. And during this point, it is latent heat of fusion absorbed. Okay, latent heat of fusion is absorbed by the solid. Alright? Now, the energy, this latent heat of fusion, which is the energy absorbed by the solid, is for what? Since it is melting, we say it is to break intermolecular forces. It is to break intermolecular forces for it to change the state from solid to liquid. Okay, from solid to liquid. You need to break the intermolecular forces. And to break these intermolecular forces, you need a lot more energy. That's why during this 3 to 7 minutes, where the temperature stays constant during this melting process, the energy absorbed by the substance is much greater than from A to B when temperature rises only. The energy absorbed from B to C has an extra work to do. It is used to break intermolecular force. It's a tougher work to do. That's why the energy absorbed during this process, a melting process, is much more than A to B. Now going to the right side, during this part, what do we say about kinetic theory? What can we say about the kinetic theory? In terms of the movement, the molecule vibrate at constant speed. Do you know why it's constant speed? Because the temperature stay constant. The temperature stays constant. Therefore, since there's no change in temperature, at this state, the speed is constant. There's no change in speed. Now, number two, concerning the space between them, the space increase because the state has changed from solid to liquid. From solid to liquid state, if you remember the molecular structure for liquid, the molecules is slightly further apart. If it has changed to liquid, the molecules has changed from very closely packed to slightly further apart, such that the molecules now is able to move in cluster, gliding across one another. That is liquid state. So the spacing between the particles increases. Now, having said that, let's look at what happened to the internal energy. For kinetic energy, therefore I say, for kinetic energy, since the speed of movement is constant, there is no change to the kinetic energy. Okay? If you compare to the answer above, just now the molecules vibrate faster, that's why kinetic energy increases. But now, since molecules remain, the speed of movement remain constant, therefore the kinetic energy remain constant. But for the potential energy, the spacing between them has increased. Therefore, we say the potential energy increases. And since total energy is made up of both kinetic and potential energy, so long one of them increase, the internal energy increase. So I would say that the internal energy has also increased because the potential energy from B to C during this melting process, the potential energy increased. Therefore, it contributes to the internal energy increase, although kinetic energy remain constant. Now, this part is very, very important. You notice I put a star here. Very often, your O-level question asks about this part. From B to C, why did the temperature stay constant? Why does it stay constant? Okay? The reason why it stays constant is because energy, although it's being heated and energy, the latent heat of fusion is absorbed by the solid. It was used to what? It was used to break intermolecular forces to change the solid to liquid. It wasn't used to increase the temperature. That's why temperature stay constant. Now, if you understand this whole part of it, it is good enough for you to understand also why temperature stay constant for boiling. You will know how to answer for boiling. So check it out yourself. From Y to Z, why did the temperature stay constant? Even though latent heat of vaporization is absorbed by the substance. Can you regurgitate the answer yourself? The reason is because the energy absorbed is used to break intermolecular force of the liquid as it changes, as it boils and change to the gaseous state. Okay? It need to break, the energy is used to break intermolecular force again. But this time is for boiling. The change of state is from liquid to gas. Now, if you know how to explain all this, the reason is totally opposite for cooling curve. That's why when it comes to cooling curve, I have given you all the answer clearly here already. If you check it yourself, you will realize that everything that is described here in this 3 column is the opposite of this heating. For cooling, everything is opposite to heating. But I still want to refer you to the graph. Let's not skip the graph. Cooling curve is still important. Okay, so let's take a look at this right-hand side again. This right-hand side talk about cooling curve. Cooling means temperature decreases. If temperature decreases, it means energy is given out this time. It's not absorbed. For heating, temperature need to rise. So energy is absorbed. But for cooling, temperature decreases. Energy is given out. So I'm going to draw the arrow this way. For heating, temperature, energy is absorbed. Okay. Sorry. Energy is absorbed. But for cooling, energy is given out by the substance. Okay. For heating, energy is absorbed by the substance. For cooling, energy is given out or released by the substance. That's how the transfer is happening. Okay, so continue on the cooling curve. You will see during freezing and condensing, this part, since temperature is dropping, you can only see freezing or condensing. Temperature, again, will stay constant. It will decrease, but when it reaches freezing and condensing, temperature will stay constant and the state changes. This time the state change is known, at this point, is known as freezing or condensing point. Okay, so again, let's talk about some important terms here. From H to I can see temperature drop. So we say energy is given out or released by the substance. But during I to J, something happened, right? Solids start to appear because freezing is happening. This is the period where it is freezing. You may want to write it down. It is freezing. Okay? Since we are talking about solid changing to liquid changing to solid, so it is freezing. And during freezing, what energy is given out this time is not normal kind of energy. It is called latent heat of fusion. When the changes is always between liquid to solid or solid to liquid, the term used is fusion. Latent heat of fusion is given out. And again, this time the energy given out at this point is much more than the energy given out from H to I. I repeat, the energy given from I to J is much more than energy given out by H to I. Okay, so reason again later we will talk about it. Why during this period energy given out is much more. It's the opposite of breaking intermolecular force. This time I to J, it is forming intermolecular force. You need to bring all the molecules closer together. And to do that, you need to release even more energy. The substance need to release and give out more energy in order to pull the particles closer to form solid this time. All right. Now from J to K, it has totally become solid. Only one state left. All right. Similarly, looking at the graph on the right hand side, it is a cooling curve, temperature is dropping, but it started with gas. So every time when you read the question, you must be very careful to see whether the question started with liquid or started with gas. If it started with liquid, then this part here is freezing. If it started with gas, then the MN part here is talking about condensing. You may want to write here, since it started with gas, then the bottom part of it, I should write condense. Okay, it's condensing. All right, condense. And again, during condensing, the term used this time, the energy has to be given out, but the term used is latent heat of vaporization is given out by the substance. Again, we have freezing point, but freezing is purely used for water. Ice, water change to ice. But sometimes wax can also become solid. And we don't say wax, the liquid wax freeze. We say the liquid wax solidify. So freezing point is also termed as solidifying point. Okay, so in this graph here, the freezing point is 50 degrees Celsius. What about the condensing point? It is 80 degrees Celsius. Okay, so that's what you must be able to tell from heating curve and cooling curve. And sometimes be careful about the x-axis. Sometimes the time given is in second, sometimes the time given is in minutes. All right, be very careful about the units used, because you need to use the graph, the timing for calculation at times. Later we will see one example given behind. All right, now I refer you this cooling curve, or H to I to J, and J to K, to the second page, 3 column again. Now this one you will go back and read it yourself. H to I, liquid is cooling down, temperature decreases. Now all this is opposite of heating, just now A to B. This time, this point very, very important. You may want to mark 2 star. Okay, very important. Highlight this point, please. Highlight, very, very important. I will highlight with a ruler. Energy. Why why temperature is decreasing? Because energy is released to lower its temperature. Similarly, two star here. This point also very important. This point here. Okay, sorry. Okay. This point here onward. Energy is released. Why, while energy is released, the temperature remain constant? Why? Why temperature remain constant? It is often asked, why why temperature remain constant even though energy is being given out by the substance? Normally, when a substance give out energy, the temperature should drop. But why in this case, I to J, the temperature remain constant? Because the energy is released by the liquid to what? To allow intermolecular bonds to form as it changes to solid during this freezing process. All right? If you can say that, it's good enough. Now, again, the middle column talks about, this column talks about the kinetic theory part of it. Molecules vibrate slower. The spacing now come closer to each other, decrease. Therefore, internal energy decreases. Okay, the internal energy of it decreases. So in total, hold on, in total, therefore, let me write this part. In total, therefore, the internal energy decreases. Okay. Okay. So internal energy decreases because both Ke and both the Ke and the Pe decreases. Okay, so same reason for here. Since during when the temperatures remain constant, again the speed of movement remain constant, so no change in the kinetic energy. In the kinetic energy, during freezing, okay, during the freezing process. But because it changed to solid, the molecules has come closer together, and therefore potential energy decreases. When either one of these decrease, the internal energy decrease. All right? Okay. Let me take out this one. And remember I mentioned about there's a little part that may need calculation. If you are given the graph, heating curve or cooling curve, and you know very well that there's timing involved, just now we saw, right? There's timing involved, 3 seconds, 3rd second to the 7th second. The time involved in melting was 4 minutes. Okay, 3 to 7 is 4 minutes. It took 4 minutes. Okay, 4 minutes for the melting process. Now when temperature, this timing is involved, and you know the power of the heater. Let's take a look at this. When power of the heater is given, like 200 watt from the graph BC. Let's look at graph BC again. From graph BC. So BC is our first heating curve graph. Now calculate the amount of energy used in the melting process. So if I go up to the graph BC, look at BC, I can see that it takes 4 minutes. Okay, 4 minutes. Now using this 4 minutes time, and so the time given is 4 minutes for melting. Use in this melting process, what is the energy absorbed? What is the energy absorbed by the heater? Again, assuming that the system is ideal, the energy given out by the heater is all absorbed by the solid during the melting. I would therefore calculate using this formula, energy used by the heater is actually E equal P times T. So E equal P times T, meaning 200 watt times the 4 minute. But remember, to get answer in joules, you cannot put 4 minutes. You have to put 4 minutes times 60 seconds. Okay? 4 minutes times 60 seconds. When you have that, you will know the answer. You can get the answer calculate that yourself. You will get the answer in joules. Okay? So the formula, at least you need to know when it involves the heater, is E equal power times time. And let me use a different color here. Since we are talking about energy in joules, therefore power must be in watt and time must be in second. All right? That's where this formula came from when we calculate the third formula involving heater in the part on heat capacity, specific heat capacity, specific latent heat of fusion, where heater is involved. We are always talking about E equal PT, power times time. Right. We are coming to an end. After talking about freezing, melting, boiling, condensing, there's this little part later we have to talk about evaporation. Now this part I will just quickly skim through because there are 6 differences about boiling and evaporation, which you need to memorize at least 3 of them. Very often, if there's a question that asks you what is the difference between boiling and evaporation, you must be quick enough to recall at least 3 of them. Now, knowing that there are 6 differences, it means boiling and evaporation are very different. Although the change of state is the same. Both boiling and evaporation have a change of state from, both boiling and evaporation have a change of state from what? Liquid to gas, right? From liquid to gas. But they are very different when it talks about the physical properties. So if you recall, for boiling, bubbles are seen, but evaporation, no bubbles seen, right? Boiling can only cause heating effect. If you touch boiled water, water that's boiling, you are burnt, okay? It burns your finger, so it causes heating. But for evaporation, when you perspire, when your sweat on the skin, when the sweat on your skin evaporates, it gives you a cooling sensation. Okay? Similarly, if you have a bit of kerosene spill on your hand or perfume and you blow on it to evaporate very fast, it will give you the cooling sensation on your skin. So evaporation causes cooling. Later, there's a need to explain why evaporation causes cooling by using the kinetic theory of particles to explain why this happened. All right. Now, boiling is a very quick process. You put some water, you boil it disappears. But evaporation can take 1 or 2 days. If you have 1 bowl of water leave on the table at room temperature, it may take 1 or 2 days to evaporate. It's a slow process. Now, other than that, another 3 that you will want to take note is boiling occurs throughout the water. You can see bubbling throughout the water, but evaporation occurs quietly on the surface. It's very quiet on the surface. The next day you realize, the bowl of water disappeared. Okay, it's a very quiet process. Not just that, boiling occurs at a fixed temperature. For water, boiling only occurs at 100 degrees Celsius, right? But evaporation occurs at any temperature in the room, under the hot sun. So it's regardless of the temperature in the surrounding. It can happen at any temperature. So that makes evaporation different again. One last one. For boiling, energy is from a source. The energy absorbed by the water is from the stove or Bunsen burner, a source that is heating it to make the water boil. So it's from a source. But evaporation can happen quietly if you leave a bowl of water there. Where does it get the energy from? The surface molecules absorb the energy from its surrounding. It can be from the bowl, it can be from the rest of the liquid at the bottom of the surface, it can be even from the air particles that is knocking on the surface molecules. So it absorbs energy from its surrounding. Okay, if your sweat on your skin evaporate, for it to evaporate, it must have absorbed enough energy from your skin and surrounding. Okay, for it to evaporate. So later we talk a little bit about the kinetic theory on that. Okay, now look at the graph on the right just to see whether you know how to draw. Okay, it also involves some knowledge of drawing. Can you sketch the heating curve of ice as it is heated from 0 to 110? Okay, let's do this. At minus 10 degree, heated from minus 10, not 0. Let me correct this. This one is minus 10 degrees Celsius. Okay, correct this. So from minus 10, it was still a solid. So the solid temperature would have rise. But when it reached 0 degrees Celsius, the temperature start to remain constant for a while because it start to melt. So down here is melting. Melting is occurring. When it totally changed to liquid, the temperature, and you continue to heat it, the temperature would have rise. Okay? Rise until it reached the 100 degrees Celsius. Okay, 100 degrees Celsius. The temperature remain constant again. This time, of course, it boil. It start to boil. Okay, after it complete boiling, because we are heating beyond 100, we are going up to 110. So if you continue heating it, after boiling, it all turned to gas already. You continue to heat it, then the temperature will rise a little bit more to 110. Okay, 110 degrees Celsius. So if you were to mark the state here, melting is solid plus liquid. Then this portion here will be totally liquid. At the boiling part will be liquid plus gas, and this last part is gas. All right. So you must have some knowledge of sketching heating curve or cooling curve based on the description given. All right. Now, coming to the kinetic theory, we are coming to the last part. Okay, last part of this topic. What is the last part of it? Okay, coming to the last part, evaporation. The last process, evaporation. As mentioned, okay, if I have some photo to show you, evaporation there. Evaporation involves molecule at the surface, jumping out, escaping from the bond, from the surrounding. But for it to escape from the surface, it must gather enough energy, it must absorb enough energy from the surrounding. Okay? So these surface molecules must absorb enough energy, absorb energy from the surrounding. When it absorbs enough, for it to escape, it will escape into the air and disappear. All right? Now, knowing that, that's why when comparing yourself in the water and out of the water, you will feel colder when you are out. Outside the water, you are colder. Reason why? You are so cold that you need a blanket to cover yourself when you come out of the swimming pool. Because the moment you come out of the swimming pool, the pool water that is still staying with your skin start to evaporate. When the water evaporates, it absorbs energy from your skin. That means your body loses energy. Your body loses energy. Energy to who? To the molecules at the surface. Okay, it loses energy to the surface molecules for it to evaporate. All right. Now, similarly, an elephant under the hot sun, would like to spend his time at the pool by sprinkling water on his body, because he also know that when water on the body evaporate, for the water molecules to evaporate from the skin, it needs the water molecules need to absorb energy from his body. So the body loses energy to the molecules, the liquid molecules at the surface. Okay? Since the body loses energy, it will feel colder. All right? Okay? So now, but the kinetic theory part of it, let's quickly go through. Right? So let's look at this picture here. For the molecules at the surface to escape, right, either to this or this, it must have absorbed kinetic energy. Escape molecules has higher kinetic energy, because they have higher kinetic energy. That's why they are able to escape. That means those molecules left behind, those liquid molecules left behind in the bowl, we call them the remaining molecules, they would have lower kinetic energy. When they have lower kinetic energy, guess what happened? Since they have lower kinetic energy, their movement is lower and therefore the temperature of the remaining molecule is lower. That's what gives the cooling effect. So if question asks you, explain why during evaporation the remaining molecules become cooler or the temperature become cooler, the explanation is this. Down here, I mark 2 stars. Okay, during evaporation, liquid molecules at the surface has to gain enough kinetic energy from who? From its surrounding, to escape into the air. That leaves the remaining molecules in the surrounding with lower kinetic energy. Okay? Lower kinetic energy, and hence the temperature of the remaining liquid and surrounding is lower, and they are left cooler. Okay, so this explains everything. Why during evaporation the temperature of the surrounding normally becomes cooler. In fact, if these liquid molecules leave very fast, that means evaporation is very fast. If the rate of evaporation is very fast, the bowl will become so cold that you will see condensing happen at the side because it's very cold. Okay, the surface is very cold if the rate of evaporation is very fast. Now, talking about rate of evaporation, there are a few factors affecting the rate of evaporation, and we are good to end here. Okay, the surface area. The larger the surface area, sorry about that, okay, the larger the surface area, the higher the rate of evaporation. That's why when you hang your clothes outside in the hot sun, you want to spread out your clothes, because by spreading out your wet clothes, you allow more water molecules to gather at the surface, and therefore that will increase the rate of evaporation. Okay, now moving on, the next factor is the temperature of the surrounding. Of course, the higher the temperature of the surrounding at a hotter day, right? For example, at a hotter day, then the higher the rate of evaporation. Next, presence of wind. If the more windy the day is, the more the wind will carry away the molecules on the surface, allowing more molecules at the surface to escape, hence increasing the rate of evaporation. The only one that is opposite is humidity. The higher the humidity, you know what that means? It means there are more water molecules in the air. Higher humidity means more water molecules in the air. Now, when there are more water molecules in the air, they will tend to press down on the liquid molecules on the surface of the bowl. They will press down on the surface, making it more difficult for the liquid at the surface to escape. Therefore, the higher the humidity, the slower the rate of evaporation. And that ends this topic. All right? Now, it's your job, of course, to go through and memorize all the important points where I mark the star and where I stress that it's important to give yourself a very quick revision to recall the important points. You can come to this page behind and try looking at this heating curve to answer all these blank points. Okay, all these blank points. All right. Then kinetic theory, all these blank points to see how much you understand the lesson so far. Then we talk about this definition here. Okay, can you quickly fill in, try discuss and fill in all this as much as you can. When I come back and see you in the next lesson next week, I will go through this with you and you check whether you got it right. All right, I will run through this with you. So this is for you to quickly digest and discuss with your friend next to you and see whether you can get them correct. Okay, compare the answer. Now, with whatever time left in the class or at home, it could be your homework. This could be your homework now. This is a very simple exercise on this thermal properties topic. See whether you can at least do all the MCQ Okay, all the MCQ as all right. If you have the time in the class now, you do. Okay, all the MCQ, 7 question, and I would like you to at least be able to try question 9. Try at least question 9. All right, because question 9 has got this graph with time and a bit of calculation, talking about the differences, what happened to the region. Okay, so you can skip this one, question 8 can skip. All right, and that's all for my lesson today. Thank you. We'll catch up with you next lesson.